Yeah, it says recording in progress. So it's okay. It's just for me to do it. Yeah, I
Okay.
really like your video. Like it seems like like you're a professional YouTuber. Maybe you are already. I don't know. Do you have a YouTube
Ah,
channel?
no,
No.
I don't. Yeah.
Okay. Yeah. Let me get your signature before you get too famous as a YouTuber.
Okay.
All right. Hold on a second. I'm gonna share my screen. Mhm. So, do you see the screen?
Yeah. Yeah.
All right. So what we're gonna do this what we're gonna discuss today is about binary system. It's basically how computers work. As a disclaimer, this is nothing to do with the coding itself. All right. This is
Yeah.
more like a in like very fundamental thing we can find in computer science. So it may be like too difficult sometimes,
Hmm.
like sometimes too difficult to understand because you know this is originally from the course usually for first or second or even third year of the college, right?
Okay. Yeah.
So it's very hard, I mean very difficult. And I found the same lecture in Khan Academy, and it
Hmm.
says it's an AP course, AP Computer Science. So
Okay.
if you're planning to take an AP course, I think it's good. 안녕하세요.
Ma.
안녕하세요. Yeah, one day I want pet your dog. he just disappeared, or she, I
Yeah.
don't know. It's
She.
a
Yeah.
she. Yeah. All right. Okay. So where were we? Oh, so this course is a AP part of the AP course, AP Computer Science course. So if you're planning to have a take that course, I think it's beneficial for you.
Mhm.
So let's just start. All right.
What course?
AP Computer Science.
Okay. Isn't that like only like Java though?
No, AP Computer Science is more like a general computer science, not like computer languages.
Okay.
Yeah, it's not about computer language. It's about uh, like general theory of a computer science.
Hmm.
So in computer science, there are many topics other than computer languages. Computer language is very small portion of it.
Hmm.
They don't even teach you like computer languages in college. It's more like they want you to study by yourself. They don't teach you the language if you go to the
Okay.
computer science. But anyways, so today's agenda is in two parts. One is how computers represent data. Okay, and the
Okay.
other one is how computers calculate numbers. So
Hmm.
in first part, we're gonna talk about the bit and byte. I think you've heard of it already, right? Bit and byte, right? And then we're gonna talk about like ASCII. I don't know if you heard of it, but it's a pretty fundamental thing to look at. And also in chapter, sorry, my cough doesn't go away. I don't like it. Well, anyways, so in the second chapter, we're gonna cover like binary numbers. What are the binary numbers, and what are the operations between the binary numbers. Again, this can be a little tricky, so please stop me whenever you want. All right. So when you do computer, like when you buy it or when you assemble, but like yourself, like
Yeah.
these numbers are pretty common in computer industry, right? Like 2, 4, 8, 32, 64, 128, 6, like 256, 10, 24, etc. What are the common factors among these numbers?
It's all divisible by two,
Yes, there are even numbers, right?
and
And
like if you add, let's say, do 4 plus 4 equals 8, and 16, and 32,
mm-hmm,
64, 128, 256.
right.
Yeah.
Right. That's a good observation. Um, can you think of that? You just what you just said. Can you think of it as in one expression?
Um, I'm not really sure. Maybe, yeah, I'm not really sure.
Okay. I think it's related to two. This is just a hint.
Uh,
It's a very mathematical term.
hmm,
These are. Well, I'm not gonna like.
or like
What is that?
prime numbers? No,
No, prime
not prime
numbers.
numbers.
Yeah, yeah.
Yeah, not prime numbers.
But prime numbers they start with the P, and the word I'm looking for is also start with the P.
Mm,
P.
positive? Oh, oh, powers of two.
Yes, powers of two. Exactly. Right.
Yeah,
These are
actually,
the powers of twos, right?
yeah.
So after this lecture, probably you would understand why you see so many of these power of twos in computer industry. Like
Hmm.
USB, what do you call it? Like USB sticks, memory sticks, or hard drive, even monitors and all that, right? They pretty much use these numbers, right? So after this lecture, hopefully you understand why there are so many power of twos in computer. All right.
Okay.
So chapter one, we're gonna discuss how computers represent data, right? You heard Sean's presentation, and I think you pretty much know all this about. But let's go over it anyways. So if you have a light bulb, one light bulb, how many data you can represent with these? How many information can you represent with one light bulb? How many information?
Only like one value, I think.
One value? For what is the
One,
one value?
like he said something about like ones and zeros.
Ones and zeros. So how many?
Uh, one.
If you have only one light bulb, it's only two.
Oh, two, because it's one and zero.
Yes,
Yeah.
exactly. On, no, this is actually off and on. On, no, this is off. On and off, right?
Mhm.
Like, so there are two information if we have only one light bulb, on and off, right?
Yeah.
What if you have a two light bulbs? How many informations can you represent with these two light bulbs?
Four.
Four. How? Like right on, both
Both
off,
off. Yeah.
right? So, but computers, they don't made of a light bulbs, right?
Hmm.
They they just they have bunch of like they consist of a bunch of circuits, right? So let's just think about like wire, all right? If you have only one wire, how many informations can you represent? If you have one,
I think two.
two, right?
Yeah.
One on and off, right?
Hmm.
What if you have a two,
That's four.
four? Let's say on is one and off is two. Let's just say it, okay? So both are off, bottom is on, upper is one, and both are on, right? So there are four different information you can represent with the two wires, right? What about three? Can you guess?
I think 12.
12?
Oh, no. That's two for each one. Six.
6? All right, let's just count it. Let's just count it. All right. 0, 0, 0. All right. And 0, 0, 1. And 0, 1, 0. 0, 1, 1. Right? The
Yeah.
up one is all off for now. So let's turn it on now. 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, sorry, 1, 1, 0, 1, 1, 1. Do you have anything else?
Uh, no.
No. How many?
That's
That's,
one, two, three,
yeah,
8.
that's 8. 8 different information you can represent with the 3 different wires, right? So let's go back to the 2. 2 is equal to power of
2.
1.
Oh,
I mean,
2 to the power of what?
2 to the power of 1. Yeah, 2 to the
Yes.
power of 1. What about 2? I mean, what about 4? 2 to the power of
2.
2, right? Here, what about like 8? 2 to the power of
3.
3, right? We all
Yeah.
learn it from like, I think it's 5th grade or 6th grade, like the exponent, right? So then what about we have a if we have a the wire 6, how many informations can we have? Probably 2 to the power of
6.
6, right? Because we have a 6 different thing. So these are the numbers, right? 1, 2, and these 3. So if we have 6 different wires, then the information that it can represent is 2 to the power of 2, which is 64.
4. Yeah.
Right? We are meeting now we are seeing the power of 2, powers of 2, right? All those numbers, right? This is because the way the computer represent their data is in this way, right?
Yeah.
All right. But computers, they don't consist of like these thick wires, right? You know it because you assembled it, right?
Yeah.
So the amount of the wires they have is humongous, right? There are many different wires. You can't really throw it. I think this is pretty simple too, compared to the real computer, right? I just Googled it and found the image, but the real computer should be more sophisticated than this, right? So although the computer can only understand on and off, right? Only two sort of information. Only computer can understand only two information. But since you have a very many wires within the computer, right? So that's how computers understand their data, right? Any question so far?
No.
No? Good. So do you know what, have you heard bit?
No, I haven't heard of it.
Okay. It's a so what about Bitcoin?
Yeah.
Yeah.
I've heard of it. Yeah.
Yeah, Bitcoin is the word Bitcoin. The bit is come from this bit. All right, bit. So bit means individual ones and zeros. They are considered as a bit. So
Okay.
these are bits, right? So 1 or 0, they will be a bit. Then let's move on a little further. All right, how to transform electricity into numbers. As we discussed, computers only understand on and off because it uses electricity, right? And then since there are many like wires that transform, that transfers like that represent the ones or zeros, and individuals are bit. Again, individual ones and zeros are bit. Then how do computers transform those ones and zeros into numbers? All right, we're gonna cover it. So before we go in there, let's review digit first. Let's say 3,402. This is just number, the digit number.
Yeah.
What does that mean? Yeah, I know it sounds really silly, I give you a number and then, what does that mean? It's really silly question. But actually we learned it. I think it's, from 2nd grade or 3rd grade in your math course. I think we learn it. What does that mean? But since we are so familiar, so used to this representation, we just ignore what it means. But in terms of what it actually means is it's just 3 times of 10 to the power of 3 plus 4 times 10 to the power of 2 plus 0 times 10 to the power of 1 plus 2 times 10 to the power of 0. This is what it means, right?
Mhm.
So you're following, right?
I'm
So
following.
yeah, so each digit, these are each digit, right? Each
Yeah.
digit has its like own values, right?
Mhm.
So that's why we come up with this interpretation to understand what this 3,402 mean,
Okay.
right?
Yeah.
Same thing with the computers. These are individual bits. These are bits.
Okay.
Before they were digits, right? Before it was digit, now it's a bit. They are 0 or 1. Only two options, right? Because it's considered as a individual light bulb, right?
Mhm.
They only have the two options, on and off. So just like that, bits have only two options, 1 or 0. So let's say this is 1 0 1 0. What does that mean? Is 1 times 2 to the power of 3 plus 0 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 0 times 2 to the power of 0, right? You can
Yeah.
calculate it, and in digit, it is 10.
Mhm.
So this means, so this 1010 in binary form, in bits, is considered as a 10.
Okay.
What does that mean, by the way? Like, what I'm trying to say here, what's the take-home message here is computers, again, back to the computer again, they only understand what? Ons and offs, right?
Yeah.
They
Yeah.
only understand like 0 and 1. But with the combination, they can represent numbers, right?
Yeah.
Yeah. So just, like if we have let's say, again, going back to the light bulb example, if we have 4 different light bulbs, right? You can represent as a number from 0 to 15. So 10 is in between, right? So they can, with the 4 light bulbs, you can express your numbers. Am I making sense here?
So can like the different light bulbs theoretically like are the light bulbs just like can they represent any number? Does it
Any
always have
numbers?
to?
Yes. I mean, to represent a bigger number, what do you need to do? You need more light bulbs,
Yeah.
like 3 million, for example. You might need a 10 or 12, 12 light bulbs if you want to, represent like 3 millions.
Hmm.
But, like it doesn't matter how many how big is your number is, if you can make a bigger light bulb, I mean, like more light bulbs, you can represent any number. That's the whole message,
Okay.
right? So this is a binary. Let's just change it. Binary 0 is the based on this equation. Binary 0 is in digits is a 0 too,
Yep.
right? What about 1?
One.
1. 1 0.
I think it's because when you're like uh can you go back to the previous slide?
Mm-hmm.
Is it always going to be in like 2 to the power of 2 format?
Yeah.
So it's always gonna have the 2 as the base.
Mm-hmm. Mm-hmm. Because
Okay.
it's a binary.
Okay.
Mm-hmm.
So that would mean 2 to the power of 2.
No, to the power of 1, I think that this one is.
Oh,
2 to the power of 1, right?
1.
Yeah.
Yeah.
So it's going to
So
be
2.
2, exactly. The next one will be
2, 2. Wait, I'm having trouble seeing that one right there. Can you? I'm having trouble seeing the numbers on. I'll just restart my Zoom page.
did it help?
Oh, wait, yeah, that's better. That's better.
Yeah, sure.
So if that's 2 to the power of 1 times 1,
Mm-hmm.
it's
Yeah.
2. And
2
then,
to the, sorry. So I'm sorry.
so
1 times 2 to the power of 1, right? Plus 1 to the power of 0 is 3, right?
mhm.
Yeah. So things like this. It keep going. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right?
It's 15 because so that's 2 to the power of 2 to the power of 1. The tens place the 2 to the power of 1.
Mhm.
Then the like the hundreds basically
Mhm.
is 2 to the power of 3, then 2 to the power of 4, and
Yes.
so forth.
Yeah.
Okay.
These 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3. This is the interpretation of these things.
Mhm.
Yeah. So that's why it's
Yeah.
15, right?
Mhm.
So this is how computers, again, you don't have to memorize all these, right? It's just, reference. I just show you as an example. But the message is computers now understand numbers, right? Again, what's the basic? Computers only understand ons and offs.
Yeah.
But now they can understand the integer, the values, right? This is an exciting. I mean, like this is exciting thing because this is a breakthrough back in 1960s when the computers were invented. This is a very very core thing in when the computer was invented. Like people were so excited. Why? Because they could represent the numbers with the electricity, or let's say light bulbs, right? So
Mhm.
back then it was so exciting. Another thing to remember is this. What's the 1 kilometer? Do you remember in terms of meter?
I don't really use kilometers, so
It's fine. Like
yeah. I think
um
it's like half a mile. I'm not really sure.
no, not meter. I mean not mile. In terms of meter.
Uh
My
I don't
question is
know.
my question is what does K stand for?
Okay.
Yeah. Yeah, let's say what about 1K dollar, or I don't know, dollar.
Yeah, 1,000 meters.
Yeah, my bad. My bad. Like this PowerPoint slide, like they just advanced without my permission. So this K means 10 to the power of 3, usually.
Yeah.
Yeah. Like 1 kilogram is what? 1 kilogram is like 1,000
1,000 grams.
grams, right?
Yeah.
And 1 kilo dollar is
$1,000.
$1,000, right?
Yeah.
And let me erase it because you screwed up. I mean, I screwed up in presenting this slide. But yeah, this is the thing. What about? Come on. Yeah. What about 1 kilobyte or kilobits?
It's 1,000 bytes.
Are you sure?
Uh,
We haven't touched the bytes yet, but you know the byte, right?
yeah.
Yeah. It's a computer unit, right? Are you sure? 1 kilobyte is 1,000 byte.
I think it's some other value. I'm pretty sure.
Yeah.
Like below kilo.
Actually, I have an answer which is a little different than 1000. The answer is, why doesn't this thing work? The answer is 1024 byte.
Is that like 2 to the power of
2 to the power of
or 8, 6, 2. I think it's 8 to the power of 8.
some more. Come on.
Is it 2 to the power of 9?
10. It's 2
2
to the
to,
power.
okay.
Yeah. 2 to the power of 10.
Oh yeah.
Yeah.
Okay.
It's okay. Don't worry about it. I was just joking. But there. So to have this, the reason we have a k usually is to shorten the numbers, right?
Mhm.
Like it just approximate the thing. But in computer, 1000 is very hard to express. Instead, 1024 is easier because we already have a 2 to the power of 10, and the computers are since we are working on the power of 2 numbers, right? Powers of 2, right? So 2 to the power of 10 is a lot more easier to understand. So usually 1 kilobyte is a 1024 byte. This is just common sense knowledge, too good to have, right? So
yeah.
And then this slide, you can ignore it, but I'll just throw you this information because this is more like a graduate school level information. But I'm gonna throw it at you anyways. If you don't like it, just skip it. It's fine. But this is an amount of information. Some 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 people or some scholars or some researchers, they like to know how much information in the data set, right? So 2 to the power of n is the one that we just discussed, right? N is probably like number of light bulbs, right?
Mhm.
If we have like number of n light bulbs, we can express this much of information with those light bulbs, right?
Yeah.
Yeah. And then some people, I mean, this is good, but it's too big. Numbers are too big, right? So people like to take a logarithm. Do you know this thing? Log?
I think I'm learning it next week.
Oh, next week. Okay. It's right on time, right?
Yeah.
So if we take a logarithm on this thing, just n is left, right? So this is a bit. We just discussed, right? So let's say to measure the information of the data, whole data set. So somebody will ask, what's the amount of information? And then researchers or scientists, they will answer, oh, the information embedded in this data set is like 100 bit. I'm not talking about the data size, about it's more like an amount of information. It's called, uh, it's called entropy. You will forget about everything. You can forget about everything, but it's good to remember the name entropy is a amount of information. Again, this is a graduate school level lecture, so you can forget it. But it's something good to something good to remember. All right.
I think I heard of it in like science.
Yes. Entropy is used in many different ways. Um, like in thermodynamics, they use use it as to represent the what is this, the wilderness, what do you call it, the chaos, how unstable the system is. But in information technology, we call it to represent the amount of information, right?
Like,
So
because I think I'm not really sure. I learned this like a year ago, but like
Mhm.
the more crazy things are, the more like disorder there
Yes,
is,
yes.
the higher the probability.
Yeah. I
Yeah.
like it. I like it. Since you already know it, let's think about it. Tomorrow, the sun will rise from the east.
hmm
How much information does it the statement that I just said have?
The sun.
Yeah, the sun will rise from the east tomorrow morning.
That's
How,
4.
no, I mean like in general. Like I'm not saying it's countable. Is it meaningful statement by the way?
Uh, Not really.
Not really, right? It's
Yeah.
it's gonna do it anyways, right?
hmm
So the probability of the what I just said is high or low?
High.
It's a very, very high, you know.
Yeah.
I can say it's like 100%, very close to 100%, right?
hmm
So if it is very close to 100%, the information is what? Very low.
hmm
It's the information wise, it doesn't mean anything, right? It's gonna do
Yeah.
anyways, right?
Yeah.
But if I flip the coin, the
hmm
fair coin, and then the tail will be show up. Is it good information or bad information?
I think it's bad information
Why?
because it's 50-50, I guess.
Yeah, I mean,
Yeah.
let's say it's true. Let's say it's true. Just
hmm
like when I said, tomorrow sun will rise from the east. That's true,
Yeah.
right?
hmm
Just like that. Let's say if I flip the coin, the tail will show up. Let's say it's true. Is the information valuable?
Uh, yes.
Yes, right?
Yeah.
Why? Because you can use it as a gamble, right?
hmm
Like you can bet on it, right?
Yeah.
Of course you cannot do it, but if I can, right?
Yeah.
So the probability, in terms of the probability of getting head or tail is 50-50.
hmm
The chances are the same, right?
Yeah.
So the randomness is pretty high,
hmm
right?
Yeah.
So when the random is high, the amount of information is very high too. Okay,
Okay.
I think we should stop here because like this, we're going too far. But this is an information theory.
hmm
I think if you major in computer science or electrical engineering or any engineering, and then if you go to like graduate school, and then I think at second year of your graduate school, like during your master, you will learn it. So
Okay.
we don't have to like pass all the way to the graduate school. So we better stop here. But remember, lower probability, higher information, and higher probability, low information. Think about just what I just said, like tomorrow, the sun will rise from the east. That's information wise, nothing, right?
hmm
And then probability wise, very high, right?
Yeah.
Okay, now no more, no more graduate level. All right, let's go to the byte. Since you already know the byte, byte is a group of bits. It's a group of bits. How many bits are there?
There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15,
What?
16. 6,
No, I
6.
mean
No.
like bit. Bit means, like number of bulbs.
Oh, there are 8.
Yeah, there
8
are eight.
bulbs.
Yeah, there are 8 bits.
Yeah.
8 bits is a byte. So a byte consists of 8 bits, right?
Mhm.
Do you want to know why 8? Like in particular, why 8? Eh, How many information can you represent with the 8 bits? It's a 2 to the power of
3.
what?
2 to the power of 3 is 8.
No, no, no. Like 8 bits. Like with the 8 light bulbs, how many information can you represent? 2 to the power
That's
of
8.
8, right? Which is 256,
56.
right?
Yeah.
That's number of information you can represent with this byte, right?
Mm-hmm.
But why byte? I mean, why 8? Why 8 bits? Why?
Um, I'm not really sure.
Yeah, it's a complex question actually. So back in 1960s or 70s, most like 60s,
Mm-hmm.
computers invented, right? And the inventors thought this will be enough to represent the characters, right? If the computers were invented in China, if things will be different because there are characters like so many, right? Thousands of thousands of characters there, right?
Yeah.
But since the computers were invented in the US, people thought 256 is enough to represent the data, represent the characters, including like uppercase, a lowercase, and some special characters, right?
Mm-hmm.
Yeah, think of your keyboard. How many keys are there? Less than 100,
Like,
right?
uh-huh.
Yeah, less than 100. Or oh yeah, maybe a 108. 108 keyboard layout. I kind of remember that is. But it's still like more or less 100, right? So people
Yeah.
thought, the inventors thought, okay, 8 bits, which is like 256, will be enough to represent all the keys, right?
Mm-hmm.
And then they
Yeah.
actually made this ASCII table. This is called ASCII table. ASCII table is they had a mapping between the decimal number from 0 to 127
Mm-hmm.
with the characters here. You see the characters, right?
Yeah.
Like all the special characters, and then here even you have a capital letters, and here you have a lowercase letters, right?
Mm-hmm.
So oh, like including all those letters is still like little over 100, right? So they thought, okay, 8 bits will be enough to represent the all the characters. So let's make it as a unit, the very basic unit, right? So that's why they came up with 8 bytes. I mean, sorry, 8 bits. 8 bit as a byte. So we're gonna skip it. We're gonna skip it. Um, so that's why they came up with the thing. Have you seen this type of representation
For colors.
for
Like,
colors? Yeah.
yeah.
Like, have you done like Photoshop or anything?
I've tried it.
You tried it? Okay.
Yeah.
Can you explain what they are?
I think it just different uh numbers for like different colors. So if I were to type in like
Mhm.
E something something something, it would give me a random color.
Right, right.
Yeah.
Do you know like how it's organized, by the way?
I don't really know, but I
Okay.
think it's based on I don't really
Sure,
know.
sure. Yeah.
Yeah.
Let me cover this thing then. All right. So one, I'm just playing digits that we just use it. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then what?
Uh 10?
10? Okay. Yeah, it's a 10. But in
Yeah.
digit, you only have these 10 numbers, 10 characters, right?
Mm-hmm.
But I want something more. I want something more. So, it's just gone. I don't know. All right. Then this is a 4 digit. You have a 10 different numbers, different characters to represent numbers, right? And I want some more. So after 9, I started to use A, which will represent 10 in digit, and B, which will represent 11, C, which will represent 12. Just like, Queen, Jack, No, Jack, Queen, King in cards, right? Just like that, we just use an alphabet to represent these numbers. D to represent 13, E for 14, and F 15, right? So how many numbers here? 16 numbers, 16 characters to represent the thing, right?
Yeah.
And then what's the power of what? I mean, 16 is the power of what? Power of 2 of what?
4.
4, right? Which
Yeah.
means there are 4 different digits. I mean, not digit, 4 bits to represent this number. So this is called hex number or hexacode. Hexacode. You don't have to know, but this is for just like I brought it because it's gonna be fun to understand these color codes. Okay, so these
So
6 digit. This is R and G, B. The colors are a mixture of RGB, red and green and blue. Have you heard that?
oh yeah.
Yeah. So these individual numbers are represent the intensity, the brightness of the a portion of red, portion of green, portion of B, right? So, well, anyways, this is just like for fun. All right. So far, we discussed how computers represent the data, right?
Yeah.
So we discussed about like numbers, like how computers represent the numbers, and also we discussed how computers represent the characters using the bytes, right?
Yeah.
Using the ASCII code. Now we're gonna discuss a little bit about like binary operation, and at the end of the session, I will give you a homework. Sorry, but homework is inevitable, and I know you are enjoying it. So yeah, so let's do it. So operation, What I mean by operation is plus, minus, and multiply and division in arithmetic operation, right? But computers can do it, right? Can
Yeah.
computers do the plus and minus?
Mhm.
Not yet. We haven't learned it yet, right? I mean,
Oh, okay.
of course in the Python level we have, but in terms of a binary system like ones and zeros, we have not covered it. And then we considered um, so there are only couple operators available in circuits: AND, OR, XOR, and NOT. These fours are the only operators that are available. I will get to the point that like what do they mean. So here, these are the inputs. If you have two inputs, A and B, right? And then
Yeah.
these are the operators. Just like the plus and minus, the multiplication and the division in arithmetic sense. And these are the inputs. Let's think about the AND first. AND spits out 1 only if both inputs are 1, right? So 0, 0 will, if the inputs are both 0, output will be 0. One of them is 1, doesn't matter, still 0 and 0. And only if both inputs are 1, it will spit out 1.
Isn't this just like if statements?
Yes, yes.
Kind of.
It's exactly like a if statement. But this is not the computer language if statement, right? This is more
Yeah.
like a very fundamental circuit level or assembly level statement. Okay,
Yeah.
and or is more like a like any of them. If any input is 1, then it spit out 1. Right? You following? Right? These
Yeah.
three. And XOR is they spit out 1 if they are different. It's kind of complicated. So If they are both same, 0 and 0 and 1, they are 0. The outputs are 0.
Wait,
So
can you
the
explain that one more time?
yeah, XOR spit
Yeah.
out 1 only if the inputs are different.
So it would only spit out 1 if they're not 1.
No, inputs are different. 1 and 0 and 1 will spit out 1. And 1 and 0 spit out 1. But 0, 0 or 1 and 1 spit out 0.
So would 2 and 2 spit out 0?
There is no 2. This is a binary.
Oh, yeah. Okay.
Yeah.
That makes more sense.
XOR makes sense?
Yeah, it makes sense.
All right. And NAND, this is a little complicated too. This is a NAND represent not AND. They just put the AND from not and then made that NAND. I don't know who made this thing, but this guy is so crazy. So anyways, NAND is spit out 0 only if both inputs are 1. So it's exactly opposite of AND, right?
Yeah.
You see? Yeah. So these 4s are the only operators in the binary. So with these operators, computers can create plus, the arithmetic plus and minus. Did you copy the last sentence that I said? Only with these operators, computers make the arithmetic operators like plus, minus, and things. They can't do this thing otherwise. All right.
What
So
does, like, how do you get from this
Mm.
to like multiplying?
yeah, that we'll get there. We'll get there. We'll get there. That's your
Okay.
homework, actually. That's your homework.
Yeah.
So no, your homework is a little bit easier than that. So let's revisit the arithmetic operation in digits. All right. So this one. Okay, it seems like we are in the first grade of
Yeah.
elementary school, right? How do you compute 9 plus 1?
You take 9 and you take 1
Mm-hmm.
and you add them together.
Right.
Which gives you 10.
10? Are you sure? You skip a lot of steps actually.
Um,
Not why 9 plus 1 is 10.
because
Yeah, it's getting more philosophical question, right? Hope you enjoy it though.
9,
Mm-hmm.
the digit. So wouldn't that be A? 9
Uh,
plus.
in hexacode, yes. In hexacode, that's A, but we're talking about the digit here.
Okay.
What's the mechanism here? What's the mechanism? Like you know it, but you didn't say it. So I want you to say it.
What do you mean by, like, what's the.
The mechanism is, 9 plus 1. There is a hidden, when you said 9 plus 1 is 10, right? You said it, and then I think it's correct. But there are hidden steps that you didn't say. We obviously know it. And, since everyone knows it, we just skip it. But I want you to, let's go back to the second grade or first grade, and then let's say it like in more detail.
Okay. So
Alright?
first you're gonna take the digit 9,
Mm-hmm.
which is from 1, 2, 3, 4, 5, 6, 7, 8, 9.
Yeah, that's cool.
Then you're going to add it to 1 by,
Mm-hmm.
and adding means to take one number
Mm-hmm.
and another number
Mm-hmm.
and basically count the digits up from 9. So
Uh-huh.
let's say if you do 9
Mm.
plus the digit 1, you
Okay.
would count 1 from the digit 9.
I see. So you're using this line approach, right?
Yeah.
Yeah. So this is a 9 and you just one step ahead, which is 10, right?
Mhm.
Yeah, this is a good answer. This is a good answer, but as you expected, I want something else.
Yeah, okay.
Yeah. So let's just hang on to this equation. Let's just hang on to it. Yeah, I don't want to, like to tease you more. So let's just go into it. All right, 9 plus 1. How you calculate usually is 9 plus 1 is what? 0.
Ah.
And then you carry over 1 here. Right? Do you remember? You carry over, and then since there is no tens digit, you just put 1 here.
Oh, yeah.
Right? Let's go back to the let's do the another one. 99 plus 1, right? 9 plus 1 is 9 plus 1 is 0.
0.
Right. And then you have a 1 carry on here. Right? So another one, 9 plus 1. So it's a 0 and carry on another carry on here. So that the final answer is 100. Right? So let's go back to this truth table. And I think I need to erase it for you to actually see it more clearly. What do you think? What is the operator? What operator is most close? No, not most close. What operator is the closest one to the multiplier in this truth table? What is that?
I'd say so the AND function only puts out if they're both.
Right. So AND.
Yeah.
So your answer is AND, right?
My answer is AND.
AND is the closest operator to the multiplier, right? That's a correct answer. What about plus?
Plus, I'd say or.
Or is good, except the last thing. 1 plus 1 should be what?
2.
But we don't have a 2 in binary thing.
1, 1, 1. 1 plus 1.
1 plus 1 is, I mean, in digit is like it's a 2, right? But in digit, 1 plus 1 is 1 0, right?
Oh,
so it should be, so it should be 0. And then carry over. You know what I mean?
Okay.
Yeah. Like let's do this thing again. 1 plus 1 is 2 in digits, right? But in binary, 1 plus 1 is 0 because it overflows, right? So it overflows to the darn it. I don't know why this thing is keep happening. So 1 plus 1 is 0. And then you have another carry on here. So it should be 1 0.
Yeah.
Okay. So the closest operator in binary operation to the plus in arithmetic operation is XOR. Right?
Because XOR it only spits it out if they're different.
Right. Exactly. This is more like this is more like a plus, right? And this is more like a multiply. Okay. And my homework for you today is actually design plus operation in when you have a 4 4 digits. You want to do plus. Let's say these are, the numbers are like 100, something like this, right? I want you to, like, how we're going to combine these two to the answer. And you have a carryover, you consider carryovers and all that. Do you think, can you do it?
I think I'll do it today.
No. You are too hard, man. Like, don't do it. No, I'm just kidding. But yeah, do it. Feel free to do it. I mean, again, this is a college level course. All right. I just gave this lecture. I just gave this lecture to the team meeting earlier today, right?
Mhm.
And I said the same thing. This is a homework, but it's perfectly fine even if you can't do this. I just give this homework to you to realize that, computers actually can do the arithmetic operations. You can Google it. You can, like, you can use whatever you material you can use, right? But try to solve it, and then, this is not coding problem, right?
Yeah.
You just draw, like, and take picture and send it to me. That's also fine, right? Hopefully you have a fun doing this.
So can you explain like my homework like one more time so I get it straight?
Sure, yeah,
Yeah.
definitely. Let me do this thing again. Let's say,
So what is like the thing I'm trying to design?
yeah, just plus design.
Also, do you like want the answer?
No, not the answer. Probably, like, some examples will be fine, right? I want, how do we implement this plus, right? So don't, yeah, you can just assume that, it doesn't go over 4 digits. I mean, not digit, 4 bits, right? Just assume that, it doesn't go over 4 bits. Just use these four bits, and then excuse me. So I want you to design what kind of operator to combine these two to have this answer to plus, and then how you combine these two have this answer, and then there should be some carryover here, right? And to have this answer, and then there is also carryover here, and then how you combine these two have this answer, carryover, you combine it, have this answer. Does it make sense?
Uh, yeah, I think it does a bit.
Okay, sure. Yeah. If not, feel free to give up. No, I'm trying to, like, pushing you to give up. No, I'm not doing it. But, like, feel free to Google it if you can do it. I personally did it, and I was, like, not able to search it because, like, I made this homework like in high school level, although the content was, like, like it's graduate school level, not graduate, like, third year of the college level. So you can Google it if you want. All right.
Okay, I'm not gonna Google it.
Okay. Yeah. By the way, I loved your solution. So you took an hour or so to do it.
Yeah, it shouldn't have taken that long.
So once you know the solution, it's easy, right?
Hmm.
Well, what did you feel like when you're done with that thing? How
Uh,
did you feel?
I felt kind of like stupid
Oh,
because
come on, no. Don't say it.
like it was like insanely simple.
But, like, any sort of, like, feeling that, achievement or accomplishment, that kind of thing. No.
None really.
Ah, come on. You deserve that feeling. Come on. Like, be more gracious to yourself. All right.
Okay.
All right. I think this is it for today. Just just keep doing what you're doing. All right.
Okay.
All
I'll
right.
I'll
Any
message you with
question?
the no.
Okay.
I'll message you with the answer like in like a few hours. Right.
No,
Thank you.
no.
Bye.
All right, bye. Have a good one.